Por favor, los invito a tomar asiento si son tan amables. Vamos a retomar nuestra agenda después de este breve receso, donde tuvieron la oportunidad de visitar los participantes y los stands de la muestra comercial. Vamos nuevamente a disponernos para seguir con nuestra agenda académica. Nuevamente les recuerdo que la intervención se llevará a cabo en inglés. Las personas que requieran traducción simultánea, contamos con el servicio. Pueden reclamar sus equipos al ingresar al salón con un documento de identidad. Vamos a dar paso a la intervención Experiencia Australiana en la incorporación de FNCER, a cargo del doctor Mehedi Ghazavi, Dozein, Lecturer Assistant Professor, Electrical and Computer Engineering Department de Monash University de Australia. El doctor Ghazavi es actualmente profesor adjunto de Sistemas Eléctricos y Energéticos en el Departamento de Ingeniería Eléctrica e Informática de la Universidad de Monash en Melbourne, en Australia. De 2021 a 2023 fue profesor asociado de Sistemas de Energía de la Universidad de Melbourne. Mehedi es miembro senior de IEEE y miembro del panel de Australia SIGRE C4 on Power System Technical Performance. Sus intereses de investigación incluyen la dinámica y la estabilidad del sistema eléctrico, la resistencia del sistema, la integración de las energías renovables en la red y el control de las tecnologías basadas en inversores en las redes de transmisión y distribución. Una especial bienvenida. Adelante. Welcome.
Thank you so much. Okay, perfect. Hello, everyone. It's a pleasure to be here with you today. So the topic of my talk is on dynamics and control of renewable rich power system. And I'm going to focus on Australian experiences and networks. Before I talk about this, Monash University is where I am coming from, so where I am working. And when we look at the overall world performance, is one of the top 50 universities in the world, according to different rankings. And when it comes to engineering, is #1 in Australia and 39 in the world. And it's a pleasure it's my personal pleasure to be working with some talented and smart students. And we are very involved in some projects with Australian industry, and you will see that in my presentation. So if I want to basically structure my presentation and talk for today, I'm going to have basically two sections. So one, I'm going to talk about the frequency stability and control as we increase more renewable energy resources, more distributed energy resources. And then I'm going to talk about the challenges and solutions that we actually taken in Australian industry. And then in the second half of my presentation, I'm going to focus on system strength. So effectively, the first part is related to system frequency. The second part is more related to system voltage and voltage waveform and the whole issue of voltage stability and all that. And in both cases, I'm going to focus on challenges that we have seen and the solution that taken by industry. And as I mentioned before, I'm going to focus on real-life Australian systems and experiences. So it's not just theory, it's happening. So in my presentation, I may refer to NEM, but what is NEM? So effectively, NEM is the transmission system in the eastern part of Australia and covering and supplying all the states of Queensland, New South Wales, Victoria, and South Australia. And basically, NEM stands for National Electricity Market. So when we say NEM power system, is just this part of the network. We also have Western Australia, which basically has a very small transmission network. And then this is a very long, skinny network. So effectively, the number of transmission lines that we have is sort of limited. So it's not a very mesh network that creates some sort of problem when it comes to system stability, resilience, and security. And so keep that in mind. And this network basically supply the 200 terawatt hours of electricity consumption based on the data published by AEMO. And when I say AEMO, is Australian Energy Market Operator. Is a system operator in Australia that basically operates the system and take care of all the connection thing. So it's a pretty interesting system. And to be honest, Australia is in the front line of the whole energy system decarbonization. We have been doing a couple of things for the first time in the world. And as you see from this report, please check it out. But you can see that Australia is very ambitious in terms of grid integration of renewables. And you see that we are going to have gigawatts renewable and distributed energy resources by 2050. But what does that mean? Adding PVs, adding wind units, what does that mean for system operation and control? So historically, when we look at power system, so effectively you have these fuel-based power plants featured with synchronous machines having these rotational masses. And so effectively you are going to get this AC waveform with a frequency of nominal, like 50 hertz in Australia or 60 hertz somewhere else. And then when you add renewables, so effectively you are changing the physics of network, you are changing the characteristic of the network because these technologies are being connected to the network via power electronic interface. So this may create some sort of operational challenges as you increase the number of renewables and distributed energy resources. So let me tell you what are the challenges that you may see if you add renewables, for example, here in Colombia. You want to add renewables? What would you expect to see? Potentially, all of these things that I am discussing, they are about Australia, but maybe relevant to what you do here in Colombia. So the first challenge is pretty well known, is frequency stability challenge, because as you increase the number of inverters, you take out synchronous machines, the system is losing this luxury of inertia coming from synchronous machine. So effectively, you are going to have the frequency instability problem. Because as you lose inertia, the kinetic energy, for a given contingency, this is a very nice comparison between low inertia and high inertia system. When you lose kinetic energy from the synchronous machine, following a contingency, you are going to have a very high rate in frequency deviation. So you are going to have a higher rate of change of frequency as you increase the number of renewables. And you can get this from this classical swing equation coming from the very, very traditional power system dynamics and analysis. So effectively, any mismatch between your active power generation and active power consumption may create some sort of frequency variation, and this frequency variation would be higher if you are operating in low inertia condition. So there is a higher chance of frequency instability in renewable rich power system. And let me interpret that in another way. So effectively, following the contingency, in a portion of second, you may see this very, very sharp change in system frequency. So the system frequency dynamics would be faster. The system frequency dynamics would be faster. So what is required to ensure a very stable system frequency in renewable rich power system? Maybe you can actually add inertia to the system, maybe synchronous condenser installation, or maybe you can actually provide some sort of very fast responses from some technologies, such as batteries or electrolyzers. And we will talk about this. Or maybe, if you are operating your system, if you know how much inertia you have in real time, you can basically estimate what would be the higher rate of change of frequency in your system if something goes wrong. And this inertia monitoring is very, very useful when it comes to frequency control in renewable rich power system. And this is the project that we have been doing. This is a like $3 million project that we have been doing with industry, with ARENA. Please have a look at this website. You will find the state of the art in terms of real-time inertia measurement. These sort of technologies basically is manufactured by Reactive Technology, which is a company based in the UK, and this allows you to measure inertia in real time so that you can actually put things in place if something goes wrong so that you can save your system. Another issue with operation of renewable power system is about system fragility issue. So remember the point that I mentioned, that if something goes wrong, you are going to have a higher rate of change of frequency. The system frequency dynamics would be faster. And think of system operation. Basically, you have some sort of frequency-dependent protection scheme in place, such as secondary photovoltaic tripping. In Australia, is 49.5 hertz. The nominal frequency of Australia is 50 hertz. So if the frequency goes below this threshold, TVs would trip. If frequency goes below 49 hertz, some loads would trip. So basically, just to mitigate the active power mismatch created by a contingency. Or in the case of over-frequency condition, if frequency goes above 51 hertz, some generation would trip to basically mitigate the active power mismatch caused by a contingency. So think of this. One event happened that can result in a chain of events. A couple of tripping may happen. A lot of disconnection you may see in the system. So there is a possible interaction between operation of protection and your frequency stability. Your system is more fragile as you add more renewable, as you reduce the inertia of the system. So this system fragility actually is very, very important to be managed by system operator. And let me tell you, this is not just theory. This is what we have seen in Australian network operation. This is the event that happened in August 2018. This is a separation event. So the power was being transferred from Queensland, QLD, to New South Wales, NSW. And then because of some weather condition, QNI, that's the interconnector between Queensland and New South Wales, tripped. So QNI tripped, Queensland faced over-frequency condition, generation surplus. The rest of the system faced under-frequency condition. And then 4 seconds after Queensland separation, South Australia also separated because of the frequency drop and very sharp active power rise following through the Haywood. That's the interconnector between South Australia and Victoria. And then that green curve showed that South Australia faced under frequency and then over frequency following its separation. And during this event, we had 2 system separation, 1 gigawatt of load shedding because of very low frequency condition, 200 megawatt of PV3V. One event, a lot of events happen right after that. It's a chain of events that happen. And think of this, we only had 30% of renewable. Now we are talking about 100% of renewable. So definitely, we are going to see more of these cascading events in our system. So think of this as well. So keep that in mind, this event. I will get back to this event. There are lots of interesting stuff that we can talk about. And another challenge with frequency stability and control relates to frequency regulation. Because renewables, by their nature, they are variable and uncertain. Yes, of course, we are working on forecasting, but definitely in forecasting, you still see some errors. So think of this, again, back to this classical power system dynamics. If you have a mismatch, if you have a variation in your active power, definitely you are going to get the frequency variation. And this is from the real data published by Australian Energy Market Operator. We are seeing more and wider frequency variation, minor frequency variation in Australian network because we are adding more renewable. So we are going to have higher chance of minor frequency excursion in emerging low carbon power system. What is required to basically deal with this? Maybe having some battery energy storage system can help us. Maybe if we ask all generators to provide frequency support, these are the options that we are discussing at the moment. So a quick recap. when it comes to frequency control and operation, these are three challenges that I would like to highlight. Frequency stability, frequency fragility, frequency regulation. But then what are the potential solutions? I mean, they are potential solutions. You add synchronous condenser, you add more inertia, you add more rotational masses in your system, you can basically manage the frequency control in your renewable rich system. But it comes with cost. Who pays for that? So that's also a debate on this. On mandatory frequency response requirement, this is what Australian operator is doing and is basically experimenting. Effectively, the AEMO is asking all generators to come and provide frequency control. And this is not a paid service. This is a requirement. They have to provide it. Maybe another solution is frequency response constraint in your security planning. And this is something that we have done. You don't need to connect or install new technologies. Maybe if you come up with this security map for your system, maybe you can operate your system in the safe region by co-optimizing energy and frequency control services in your planning and scheduling mechanisms. And this is what we have done. This is mathematically discussed. This is dynamically analyzed. And this is implemented in Western Australia. So this is not just a theory. This is implemented in Western Australian network, and system operator is basically benefiting from the research that we have done, and they are operating the system in a very low inertia condition. Back to the solution, how about getting some frequency response from inverter-based resources? Yes, they are inverter, they are fast. Maybe they can help us. How about battery energy storage system? Yes, it seems that battery energy storage system is a good technology to provide frequency control. But let's see how battery provided frequency control during the August event that I explained. So at the time of the event, battery was charging and then the frequency dropped. So basically you have load more than generation. So battery starts to basically reduce its active power consumption and inject power to basically mitigate the active power mismatch happened in the system. But then South Australia separated. South Australia faced over frequency condition. Battery changed its active power output and then goes to basically charging mode. So it's a very fantastic frequency control that battery is providing to the system during such a complex event. How fast it is provided. It's like a droop control of a synchronous machine, but in a very fast way. But there is a catch. There is a catch. Battery is doing what it is designed for. But battery provides this very sharp active power. This results in a very sharp change in active power following through the interconnector, and this negatively impacted the stable operation of protection. So in fact, yes, battery provides frequency control, but at the same time resulted in Haywood trip and resulted in South Australia separation. Don't get me wrong, I'm not saying batteries are bad. Batteries are good, but then the capability should be understood from a system-level perspective in the context of power system. Yes, these technologies, they are fantastic, but when you add it to the system, it's not just one battery. There are a lot of technologies. Maybe there is a negative interaction. So you gotta be very, very careful when it comes to installation and adding more batteries to the system. So effectively, this is the negative contribution to system fragility. And this is the kind of interaction that we would see as we move forward. And then we did some study. We said that, okay, let's assume that we had 700 megawatts battery in Victoria. What would have happened if you had 700 megawatt battery? And we realized that if you had FFR in Victoria, you could have potentially prevented the South Australia separation. And effectively, it's extremely important where you locate your fast frequency response, where you locate your battery for frequency control support. And again, it's extremely important to understand everything from a system level perspective. This is completely missing. I think there is a lot to do on this, that everything has to be understood from a power system perspective. Yeah, these technologies are fantastic, but then how they would operate in the context of power system. So final points on battery, you can get a lot of support from batteries, frequency regulation, virtual inertial response, but then these capabilities may be impacted by the external system, by physical characteristics of the system, and we will talk about this later in this presentation. But before we finish our discussion on frequency control, how do you incentivize batteries for providing this support? Because these supports are in a very good quality. Comparing that with synchronous machine, the response from battery is just amazing. But then how do you incentivize that? How do you incentivize this quality of response? And this is the kind of a work that we have done. This is a new market that established in Australia, is operating for like 1 month. This is the fast frequency response market, and we were very fortunate to have this collaboration with system operator. Please have a look at the report that we actually advise system operator, how do you basically establish FFR market? Again, yes, maybe some people here, they are interested to markets, but then you gotta establish the market based on the physics of network, based on the technical aspects of system operation. Building market without considering these technical aspects is just a failure. So this is also a very, very important point. And battery, yes, seem to be a very good technology, but how about hydrogen electrolyzer? In the future, we are gonna have electrolyzer anywhere. I mean, in all countries, they are talking about production of hydrogen, but these electrolyzers, they are also inverter-based technologies. They can provide some sort of support by changing their active power consumption, hence they can provide frequency control. And we did a lot of studies on this, that let's compare electrolyzer with batteries. So which one can actually help? And we realized that actually they are very good rival for batteries. So maybe provision of frequency control from electrolyzers, from inverter-based loads, from demand response, maybe we don't need that much battery. So we gotta be smarter as we think about, future power system. We gotta be smarter and basically effectively go through this pathway. We shouldn't really invest on technologies. And finally, how about the distributed energy resources from like photovoltaic? This is another project that we have done with the distribution network operator in Victoria. So AusNet Services is the largest distribution network in the state of Victoria. And in this project, we were trying to understand what are the potential capabilities in distribution network. Can you get some frequency control from distribution network? And we have done a lot of studies on this report available, but we realized that, for example, this is coming from the response of PV during the August event. Around 160 megawatt FFR was provided from distribution network in Queensland. Distributed PVs, they saved the Queensland network from blackout. And to be honest, nobody is talking about this. There is a good potential in PVs, nobody is talking about it. So we gotta be really unbiased about technologies. And what else? Many more. Many more. There are a lot of technologies. The problem is not technology. The problem is that we got to understand these things from a system level perspective. We got to analyze all of these technologies in the context of power system. So back to the principle. So when you look at power system operation and control, so you have some variables like frequency, voltage, angle, and all that. And basically you have some control like droop control, governor, all of these things. And basically with this control, you manage to keep everything in the permissible boundaries. So what are these physical characteristics? We talk about inertia. Inertia is more relevant to frequency control and operation. But how about system strength? But what is system strength? So all of these reports, highly recommended. Please have a look. all of system operators, they were trying to basically suggest what is system strength. Still, it's not very clear what is system strength. But then, generally speaking, I can say system strength indicates the system ability to maintain voltage waveform stability. Voltage waveform, so you want to have a very nice sinusoidal voltage waveform. Voltage waveform, voltage magnitude, voltage angle, voltage waveform, the shape, sinusoidal. So these are the parameters that we care about when it comes to system operation. If we consolidate all the views presented by SIGRI, IEEE, National Grid, AEMO, AEMC, all of these things, you can say this is the definition of system strength. That is the sensitivity of voltage, magnitude, angle, waveform to the active and reactive power changes in your system. So what happened to your system? What would happen to the voltages? If voltage is very sensitive, the system is weak. If voltage is not very sensitive, so effectively system is strong. And then system operators try to link system strength with fault level. That's another lecture, that how you link this to fault level. But let's accept that. Let's say the system strength is related to fault level, and effectively when the short circuit ratio reducing, you are going to have your voltage wobbly. So it's going to be more variability in your voltage, and this is not desirable in system operation. And there are different metrics basically proposed by system operators around the world. But then when we look at the very classical voltage stability, if you are operating your system here, this is a very famous PV nose curve in voltage stability. If you are operating your system here, so effectively, that short circuit ratio, that fault level is just relevant to the distance that you have with this nose point, with here, with the voltage collapse point. So to make sure that you have sufficient voltage stability, you got to make sure that you have sufficient fault in your system. But then what is the potential solution? Because this fault is coming from synchronous machines. Now we are adding renewables, we are adding inverter, we are taking out synchronous machine. Maybe you can add synchronous condenser, and this is what is happening in South Australian network. System operator invested on synchronous condenser, adding some 3 to 4 synchronous condenser, each 600 megavolt amp, to ensure that we have sufficient fault level, to ensure that we can integrate more renewables. And then what we discussed, when we talk about voltage support, so yeah, voltage would be more sensitive. The voltage stability is also a challenge in renewable-rich system. Can inverter-based resources help us? Can we get some support from inverters? And then effectively, system operators, they are defining this characteristic for inverters to get some voltage support. So this PQ capability diagram, group control, the right-through, the high voltage and low voltage right-through diagrams, all of these things basically require inverter to provide reactive power voltage support to the system under different operating conditions. This is the requirement. But can inverters do that? Maybe not. Yes, you ask them to provide this voltage support, but it may not be possible. And this is the event that happened in November 2019. Please have a look at this report as well. Following a voltage disturbance, we got around 300 megawatts of PV tripping. So they couldn't really comply with the system grid code requirements. So that's also a big challenge. And basically this, this issue of compliance primarily comes down with grid following inverters when they actually synchronize with the external system via a phase locking strategy, PLL. Maybe if the voltage is very nasty, that PLL cannot estimate the voltage, cannot maintain the inverter level stability. So what can we do? The solution may be advanced inverter control. You may heard of grid forming inverters. You may heard of virtual synchronous machines. So maybe they can help as well. Another issue that is very important and is related to voltage is about, in distribution network, you want to get some support from distribution network for the transmission network control and operation, and then you want to get multiple support, frequency control, voltage control. But then if these inverters, they are in weak distribution feeder, so effectively they want to provide frequency response to the upstream network, they change their active power, the system is so weak, the voltage goes wrong. So effectively, this negative interaction between different sort of services has to be considered when it comes to system operation of renewable rich power system. For example, in this example, you see the system stability service is frequency control, inverters provide frequency response, and that actually interacts with voltage control. And this is not something that markets see. You have market, you schedule frequency control from distribution, it goes wrong. So a very, very nice market is the market that is based on the physics of network, on the characteristics of the network. That is the market that considers the operational constraint of the network. And this is not even the inverter-driven issue. You change the inverter control, again, this problem would basically arise. This is something that has to be considered when it comes to market mechanism and structure. Another issue is a small signal oscillation. To be honest, nobody knows about this. Why we see this oscillation still is a lot of debate in Australia. For example, this is the one that I am showing here. This is the West Moree region, is northwest of Victoria, south of New South Wales, and we see this very weird small signal oscillation, and we really don't know why we see this. Again, a very systematic approach should be set up to analyze this small signal oscillation. AEMO just disconnects renewables, but of course, this is not sustainable. This creates a headache and problem for everyone and investment. And then what I would like to mention here is that we talk about the frequency stability, we talk about system strengths, but then system strength is related to voltage magnitude and angle, and you know the angle is sort of a function of frequency. So there is a zone of overlap. There is a zone of overlap between different system stability phenomena that has to be considered in system operation. Maybe you see some cascading events, some instability, some oscillations, and it's coming from the frequency aspects of the system and also voltage aspects of the system. This has to be considered in system operation. Excuse me. So there are also other challenges in operation of weak grids, such as power quality issue, because we talk about system strength, it is related to this voltage waveform. So when it comes to voltage waveform and this sinusoidal shape, definitely there is a power quality issue and concern that has to be addressed as we add more renewables. Maybe we got to think of the filters that we put at the terminal of inverters. That's also an option. Or maybe, again, back to where we locate inverters, that's also a point of concern. System protection issue, in my presentation, I tried to show this interaction, this overlap between system operation and system protection. This overlap has to be well understood as we add more renewable and inverter-based resources. System monitoring issue, that's also a point of concern, because in weak system, as I mentioned before, you are going to have very sharp voltage changes. So think of your SCADA. A SCADA has a cycle. Is it fast enough to capture those changes in voltages? Maybe not. And this is some issue that AEMO in Australia faced. Now they are working on advancing monitoring system so as to capture the real-time system variables, voltages, frequency, inertia, all of these things. And many more that has to be well understood. And all of these things, this is a project that we have done with reactive technology. This is a company in the UK that basically they are trying to run some trials in Australia, and we were very fortunate to be part of this this project. Let me tell you about this project. Of course, talking about this project, it took us 2 years to do this project, and perhaps it's like another lecture that I can actually give on techno-economic analysis of system strengths. So in this project, we tried to understand what is system strengths. So if you want to have a proper voltage in your system, when you have renewables, synchronous machines, inverters, and all that, what is really required from the principle, from the basics of power system dynamics and physics? And then how do you value that? All of this voltage control support and responses, they are not paid. But you want to ask inverter to provide voltage control? Maybe they say, okay, I don't want to do that. Do you want it like a system requirement? Or maybe you want to have a market on that. And this is why people now, they are talking about a stability market. So if you check out the AFRI report in the UK, all the discussion by National Grid, now, should we have a stability market? But then the question is, for any market, even if you want to sell Apple, think of Apple. For any market, you got to know the product, what you are going to sell. But what is system strength? What are the products that contribute to the strength of the system? These are the questions that we try to answer in this joint project between industry and academia. Another point here in my presentation, I try to highlight that, yes, we are very ambitious about renewables, but one thing is extremely important, and that is the collaboration between industry and academia. If you don't have collaboration, you are not going to be successful, for sure. For sure. So all people, they join, and then I think the outcome would be promising. So back to this, just a final report and final remark. Effectively, power system stability is defined in 5 categories. And in my presentation, I try to highlight that as we increase renewable, you are going to have frequency stability issue, voltage stability issue, rotor angle stability issue, is about transient stability, synchronism, and converter-driven stability, this sympathetic IBR tripping that I mentioned. And then another point is that we got to also think of this. This is not well understood so far. This zone of overlap between different stability types is not very well understood. What are the conditions that you may basically start with one instability type and end up with another stability type? These are the things that we should understood. That should be understood properly. And this is this is the end of my presentation. I would be happy to take any question. And if you have any questions, please reach out. This is I think my email will be provided to you, and just reach out. I would be happy to answer any question.